Hey everybody! In this lesson we're going to be solving separable differential equations. So problem number 1, given y prime or a derivative or a separable differential equation, given y prime is equal to e to the x plus 1, also given the initial condition of y of 0 equals 2, okay, notice that this is going to be an ordered pair that falls on the regular graph, the y equals graph, not the y prime, just because of the notation. All right, so to solve a separable differential equation, we want to integrate and get back to the original equation. And this initial condition is going to allow us to find the value for c that we're going to get when we do integrate. All right, so example number 1, y prime. I would suggest changing y prime, that notation, to dy dx. That way we can go ahead and separate our variables. Let's put the y's on the left and the x's on the right. So basically we're just multiplying both sides by dx. So we're left with dy equals e to the x plus 1 dx. At this point we can bring in an integral symbol because we've successfully put all y's on the left and all x's on the right. Notice we have an indefinite integral. There are no limits of integration, so that's why we're going to get a plus c over here. Remind you that this is also an integrand of 1. 1 integrates back to y, so we get y. We could put a plus c here, but we're going to have another plus c here, and they collect to just yet another constant, so no sense in putting plus c's on both sides of the equation. All right, and then here we have two terms. This is term by term integration. So e to the x's antiderivative is itself, e to the x. 1 integrates back to x. With respect to x is what we're dealing with. So plus x, and then we have plus c. So we've just now arrived at a general solution. We really want the particular solution. We can find the particular solution because we have a point that's on this equation right here. So just remember, the independent variable is x, and then the dependent is y. So just helps you remember which value to plug in for which variable. So when y is 2, all the x's are 0. So e to the 0 plus 0 plus c. So 2 equals e to the 0 is 1 plus c. Let's subtract a 1 from both sides, so c is 1. So at this point, we can come back up here and we can plug in the value of 1 for c, and we're finished. So we've solved a separable differential equation. We've solved this derivative, meaning we've gotten back to the original equation. We found the particular solution because we know the value of c. Notice in example 2 that our independent variable is t and our dependent variable is y. So we're going to try and get all the y's to the left and any t's to the right. At this point, I'd probably go ahead and separate this notation. Okay, well, we need to move this y to the left side, so we never can add or subtract to both sides when we're performing these kinds of manipulations. We can only multiply and divide. I'm going to actually leave the negative here. The little you bring over to the y side, the better. So I'm going to divide both sides by just y cubed. Okay, when I come back over here, I might bring up y to the third as y to the negative third power dy. Because I'm getting it ready for integration, we're left with a negative dt. We've successfully separated all the variables, so bring in the integral symbol. Integrating, we perform the reverse power rule. So keep the base, increase power up, add 1 to the exponent, so that's negative 2, and divide by the new exponent. We'll keep the plus c for the other side, equals. Remember, this is a negative 1, so negative 1 integrates back to negative t, and then we have our plus c. Okay, so at this point, notice that we were not given an initial condition. We weren't given an ordered pair that belongs on the original equation y. So in that case, we're off the hook and having to find the value of c. Okay, so right now we have what we call a general solution. If we wanted to solve it for y equals, we're going to have to do some more algebra. So if I wanted to solve this for y equals, get y by itself, I might drop this y to the negative 2 to the denominator. So kind of cleaning this up right here, I'd have negative 1 over 2y squared. I still have negative t plus c. Okay, if I'm going to solve for y, let's see, I might multiply both sides by negative 2. So if I multiplied both sides by negative 2, that would take care of the negative 1/2. Now we have to involve that c at this point. So we're going to multiply by negative 2. Those divide out. I'm left with 1 over y squared. If you wanted to distribute that through that negative 2, you'd have positive 2t minus 2c. If I'm still looking to get y by itself, I might reciprocate both sides. For example, just take this whole expression and put it over 1. Now let's reciprocate. So then I'm going to have y squared over 1, or just simply y squared, equals the fraction 1 over 2t minus 2c. It's awkward, it's uncomfortable, but it is mathematically correct. Now let's bring in the square root. So an even root means that we're going to have y come out, but its absolute value. And obviously over here, we can't do anything with this square root. Well, I guess you could take the square root of 1 and just have 1 over the square root of 2t minus 2c. And lastly, for this problem, we're going to remove the absolute value. So that means unless I know what the initial condition is, the ordered pair, okay, I would have to just leave my answer in this format right here, plus minus 1 over square root of 2t minus c. 2t minus 2c. Example 3, we're going to solve this separable differential equation. That means we're going to get back to y. Notice we don't have an initial condition. Our answer should contain a c in it. And I'm going to go ahead and pull the dx over to the right side. Okay, as I move over here, notice that right here I'm going to take out a y. I'm going to factor out a y. So that leaves quantity 1 minus 2x, and then of course I have the dx here. We want to go ahead and factor out that y because there's no way I can add or subtract to both sides when I'm performing these computations. I'm going to have to either multiply or divide, so it was good to take out the y. And now that I did, I want to move this y to the left side, so I'm going to divide both sides of the equation by just y. If you wanted to bring up y to the negative 1, that'd be fine. Y to the negative 1, put the differential behind it. And then I'm left with 1 minus 2x dx. And if you want to put this in parentheses, 1 minus 2x, that'd be fine too. Okay, everything looks separated, so let's go ahead and integrate. If you tried to do the reverse power rule, remember you're going to be powering up to 0, dividing by 0, so that should trigger in your brain, oh, wait a minute, this goes back to the natural log of the absolute value of y. Equals 1's antiderivative is x, and 2x is antiderivative is x squared, and then we have a plus c here. So without an initial condition, a point on the regular y graph, this is the general solution. Now, if they're asking us to put it in y equals f of x format, then we need to get y by itself. So in that case, to do a little more algebra, let's bring in the base of e. And you can only bring in one base e on each side of the equation, so that means that this whole expression becomes the entire exponent on e. We do that so that these will undo each other. They're inverses. We have the absolute value of y equals. Now, let me go ahead and write this down and then say something else in a minute. This is e raised to the x minus x squared plus c. I can remove the absolute value. So either my solution is the positive or the negative e branch, and I wouldn't know that unless I knew what the value of the initial condition was. I wouldn't know that unless I was given a point. So this is definitely one good valid answer right here. Okay, something strange that we can do, it feels a little uncomfortable because we go the reverse order in algebra, but right here, if we wanted to, okay, if I kept it absolute value of y equals, if I wanted just to put the variables on the base of e and put the constant with the base of e, I could take e to the x minus x squared and I could multiply it by another base e and I could put that term with its own base e. Think about Algebra 1, when you multiply and you have the same bases, you just add the exponents. So it's like we're decomposing, okay, this format into this format. We're kind of going backwards from how we learned properties of exponents in Algebra 2. And of course, to finish this, you'd remove the absolute value, and you get plus minus. If you're going to do this, usually we see this constant multiplier up front. So I'd put the plus minus here, e to the c, and then I'd have times e to the variable factor here. So either one of these would be correct. Given the derivative dy dt equals 2t minus ty with the initial condition 0, 4 being a point not on y prime but on the regular y, we want to solve the separable differential equation. So we're going to be able to find the value of c. If I was going to label this ordered pair correctly, remember the independent variable is t, so this would be t and the 4 would be y. Let's factor out a t. Okay, let's leave the factor t on the right side of the equation. Let's divide both sides by quantity 2 minus y. If you wanted to, you could bring this denominator up with a -1 exponent. So you'd have 2 minus y to the, my goodness, -1 dy equals t dt. All right, I would use a u substitution over here. So u is going to be 2 minus y. du is negative dy. So I'm going to have to bring in a negative here to make this du. And I'd pull a negative out here. And remember, 2 minus y is u. So let's clean all that up. So we've got negative integral u to the -1 du equals integral t dt. Okay, right here, this antiderivative is the natural log, so we're going to have the negative natural log absolute value of u equals t squared over 2 plus c. I'm going to go ahead and replace u with what it was in my u substitution. So negative natural log 2 minus y equals t squared over 2 plus c. Okay. I would encourage my students, anytime that you guys get a plus c, I would, and if you have an initial condition, which we do, I would find the c value, the value of c at the first possible time, and that's right now. So I'm going to go ahead and plug in 0 for t and 4 for y. Oh, that's nice. That's just going to go to 0, so that's just c. So let's just work over here. This is going to be negative natural log of -2, but the absolute value will make the -2 positive, so c is negative natural log of 2. Okay, so now I'm going to put that value back in right here. I'm actually going to swing around right here. Okay, so we have found a particular solution. It's just that this equation is not in y equals f of x format. So unless we're asked to go to y equals f of x, we're finished with the objective here. But let's go ahead and practice, because that's where a lot of good algebra comes in. Let's put this equation in y equals format. All right, so I'm going to go ahead and get rid of that negative by distributing it over here to the right side. Let's go ahead and bring in our e, exponentiate both sides to get the ln off of this absolute value. So e comes here, 1e each side when you bring it in. So all of that becomes the exponent. So I'll skip a line here. So the absolute value of 2 minus y is equal to, okay, so right here, I see that I have a constant right here. So I'm actually going to go ahead and take this right-hand side and rewrite it as a multiplication problem with 2 bases of e. So e raised to the variable piece, the variable term of this exponent, negative t squared over 2 times e, I'm going to give it its own base here, this term, I have to multiply ln of 2. So just double check your work. When you multiply same bases, you add those exponents, and that would get us back to the previous line. And maybe you see it, the reason I'm going to do that is because e and ln cancel, and so what I end up with is just 2 as a multiplier that I will, in my next step, put in front of my exponential function. Okay, almost there. Let's remove the absolute value, which means I've got plus minus 2e to the negative t squared over 2. I'm going to subtract a 2. So when you subtract that 2, common practice, we usually put it in front of the plus minus. So I've got negative y equals negative 2 plus or minus 2 e to the negative t squared over 2. And then lastly, we're going to, well, almost lastly, let's take the opposite of both sides of the equation. So this becomes positive y. When you divide over here, that becomes positive 2. When you divide here, those just change to a minus plus, which is still plus minus. Okay, and so now we have to decide, because we have an initial condition of 0, 4, we need to decide which one of these are we going to choose to be the final answer. Is it going to be y equals 2 plus 2 e to the negative t squared over 2, or is it going to be 2 minus 2e to the negative t squared over 2? Well, the way we're going to decide that is go back to this point right here where y is, plug in 4, and put a question mark above my equal sign, and then 2 plus or minus 2e to the t is 0. I need a 0 here. That's still going to reduce to a 0. So 4 equals question mark 2 plus or minus e to the 0 is 1. 1 times 2 is 2. So what's the only way you can get 4? 2 minus 2 or 2 plus 2? And that'll tell you which branch we want. So 2 plus 2 gives us 4. Oh, goodness, I'm going to move over here. So final answer, y equals 2 plus 2e to the negative t squared over 2. Two more. You may notice that number 5 is exactly, at least this part, the differential equation. This is exactly problem number 4 with a different initial condition. Okay. So remembering that the independent variable is t and the dependent variable is y. Okay, I'm not going to repeat all the steps of problem number 4. Where I'm going to get to is the equation after we integrate it. So I'm just going to kind of put a dot, dot, dot. I'm going to get negative ln absolute value of 2 minus y equals the t squared over 2 plus c. So go back to example 4 and grab that equation after we integrated. Now let's plug in the different initial condition. So 2 minus 3, so that's going to be -1. And t is 2, so 2 squared is 4. 4 divided by 2 is 2. 2 plus c. Coming over here, natural log of absolute value of -1 is the natural log of 1, which is 0. So this whole side reduces to 0. So in this case, c is actually equal to -2. So let's plug that back in here. Okay, and I'm going to move up here. After I bring it, well, actually, I'll go ahead and multiply both sides by a -1. Before we bring in the exponential, we need to have a positive ln. You can't bring in e unless we have just ln. And we're going to bring in a base of e, only 1 per side. Now remember, if you want to come from here down to here and put this variable term with base e and the constant term with the base e, then you're going to need to change to multiplication. So e raised to the -t squared over 2 times e raised to the second. And that's just a constant multiplier. Typically, we put that up front, constant multipliers, that is. So I'm going to do two things. I'm going to remove the absolute value. I'm going to move e squared to the front, multiply it by e to the -t squared over 2, and I'm going to try to remember to put the plus minus here. All right, let's subtract this 2 to both sides. Typically, we put that in front of the plus minus. And let's take the opposite, or divide by -1. So y equals +2 plus or minus e squared e to the -t squared over 2. And again, because we have an initial condition, we can determine, do we have 2 plus or 2 minus? Okay, so I'm going to go ahead and plug in 3 for y. And everywhere I see a t, I'm going to replace it with 2. So I'm going to square the 2 first. So 2 squared is 4. That's -4 divided by 2. So that's going to be -2. I might put a little question mark here because I'm trying to figure out which branch this is. So this is 3 equals 2 plus or minus, well, e squared times e to the -2 is e to the 0. E to the 0 is 1. And the only way I'm going to get 3 is if I take 2 and add it to 1. So now I know it's the positive branch, so final answer. All right, lastly, we're going to solve this separable differential equation. Notice there's no initial condition. Yay! I'm going to rewrite y prime as dy over dx. Sometimes it helps me to kind of slide that y off and look at this as 1/3 y. Depending upon what I'm doing, I might leave this fraction stacked as y over 3, but sometimes I like to pull that constant multiplier out front. I'm going to leave the 1/3 with the dx. Take as little as possible to the y side. Let's divide both sides by y. Bring up y to the -1. Let's integrate. Goes back to natural log absolute value of y. This goes to 1/3 x plus c. Okay, so we're done. We found the general solution, not the particular, because we don't have an initial condition, but it is not in y equals f of x format. So let's, if we want to do that, let's bring in the base of e. And for this problem, I'm just going to leave all this together. You could break it apart and give each of these terms its own base e, but for this one, I'm just going to leave it all together. Okay, let's remove the absolute value. And that's as far as we can go.